that happens within 10, 100, 1 second, the duration of the burst. That is called the prompt emission. We also call prompt emission on other wavelengths, things that are associated with it. And then comes the afterglow. Whether they're smoothly connected, directly connected, or there is a gap between them, it's not as clear usually, because the afterglow is usually measured by other means, which takes time to slew to the position where the gamma ray burst is. Today, this gap is shorter, and sometimes it is continuous, but in most cases, there is a gap between, a clear gap between what is prompt and what is afterglow. Okay. Let me start with hydrodynamics of explosions. Because a gamma ray burst is an explosion. These are all tiny, tiny pieces. What is an explosion? You release some amount of energy E at some environment with density ρ, which can be either constant or could depend on distance from the source. There are two interesting cases. One, ρ is really a constant. And the other one that the density is proportional to r to the minus 2. The density surrounding the source, where r is the distance from ρ. I didn't put the microphone. Thank you. But you all heard me, right? Okay, this is just for the recording. So the density goes down like r to the minus 2. This is what you'll get if the source, the explosion site, emitted the wind at a constant rate for a long time before the explosion. So if it emitted the wind at some constant rate m dot, and that spreads around the star, so there is a flux of mass m dot through every radius. So it's 4 pi r square v rho. And if the velocity of the wind is constant, then it means that rho goes like r to the minus 2. Okay, so these are the two interesting cases: wind or constant density. And we can have an explosion in each one of them. Okay, so explosions can be relativistic or non-relativistic. Let's start with the non-relativistic case. It's slightly simpler in some ways. If you look at times where the size of the explosion, the shock wave that came out of the explosion, is much bigger than the original size that you exploded, and it collected mass that is much bigger than the original mass of the exploding material. So for example, you explode a nuclear weapon in the atmosphere, okay? So there is the mass of the nuclear weapons, a few kilograms, tens of kilograms, I don't know. And when it collected enough air that the mass of the air around it is bigger than the mass of the bomb, you get something that is independent of the mass of the exploding stuff. So it only depends on the surrounding density. And on the amount of energy you release, that's a conserved quantity, so it affects even late timescales. Now you want to know what is the size of that shockwave that came out of that explosion after any time. And you can use the following argument. You can estimate the mass that was collected in the explosion from the environment by the density times the radius cube. You can put your 4/3 pi and all that stuff if you wish, but I will skip those. And that mass has some velocity, some kinetic energy, which you can also estimate if it arrived to radius r after a time t, then the velocity must have been, or must be, of order r over t. It doesn't have to be exactly r over t, because the velocity is not constant. Maybe this thing decelerates, maybe it accelerates, depending on the circumstances, usually decelerates. But this is an estimate of the velocity. So if you take the mass times the velocity square, maybe put a half, you get an estimate of the kinetic energy of the explosion. And there's a comparable amount of energy in thermal energy. So this is an estimate of E, the energy in the explosion. And if E is constant in time, meaning the energy you radiate away, this is the thing that we actually observe. But if what is emitted is not a considerable fraction of the energy of the explosion, then E is constant. And you can get from this a relation between the radius and the time. So you see that if the density is constant, you'll get that R is proportional to 2 to the 2/5. Right? There are 5 R's in here and 2 T's. So that leads to this. And this was used early on somewhere in the 40s to measure the energy that is coming from nuclear explosions. So that was the first application. But we have more interesting stuff. We have actually much more energetic events, not miserable nuclear explosions. And we're going to do the same thing, and they're going to be relativistic rather than this. Oh, maybe I should do also the variable density. If you plug in here that the density is going changing as a function of distance from the source, you can use any density low here, let's say R to the minus omega. Density is proportional to R to the minus omega. Plug this in, and you'll get something like the radius is proportional to T to 5 minus omega. So for this case of a wind, you'll get that the radius is proportional to T to the 2/3. Okay? Both of these, since these exponents are smaller than 1, it means that the shock is decelerating. As the explosion collects more and more mass, the velocity is going down because the total energy is fixed. I have to replace those chocks, they're too small. Okay. Okay, so what's the relativistic analog of that? This is what's going to produce the afterglow from that, or that's at least our model. So our model for the afterglow is the emission that comes from the interaction of the ejecta that came out of the explosion with the surrounding matter. Okay? And on the relevant timescale we're interested in, it's the environment that dominates the mass. So the mass is again this. This is the mass that was collected while the explosion was expanding. But now it's not times some velocity, because now it's relativistic. Okay, so it's moving almost at the speed of light. So what is the energy of something that is moving relativistically? That's a bit of a confusing thing. I hope you remember that if you have a mass m that is moving with some relativistic velocity, v close to c, then the energy of that mass is mc squared times gamma, gamma being the Lorentz factor, 1 over square root of 1 minus v squared over c squared. Beta is v over c, if I will use it later. We already mentioned beta before. Okay. This is not, okay, so in this equation, m is the mass in the rest frame of the object, is the rest mass of the object. Or mc squared is the energy in the rest frame of the object. Okay? And it is that thing that you have to multiply it by gamma. The expression I want to write in here is this times gamma squared equal E. So the first question that comes to mind is why gamma squared here? Well, the usual expression you're used to as 1 factor of gamma. So the reason is that when you have a relativistic explosion that arrives to some mass, to some radius r, running into the surrounding, let's say it is made by protons. Typical density is in the interstellar medium about 1 proton per cubic centimeter. So this is about the right scale, what I plotted in here. Each one is a proton. And once they pass behind the shock, they have also thermal velocities, which are also comparable to the speed of the shock. So the factor gamma appears twice. One in the random velocities. They also have random velocities of order gamma. And this whole thing is moving relativistically with a Lorentz factor gamma. Okay? So if you're asking yourself, what is the rest frame energy of this system, it already should contain one factor of gamma. Then the whole thing is multiplied by gamma again. Okay, so this is the relation between energy as observed in our frame, which is the constant thing. We're in an inertial frame. This is the mass that was collected, and the mass times gamma squared is the energy. So this gives us a relation between the Lorentz factor and the radius for any density profile. Let's stick for now, to make it simple, to a constant density profile, and you can take it as a homework to generalize everything I'm telling you to a wind density profile. Okay, or you can look on every paper, does usually both.
C squared.
C squared in here. Thank you. Okay, so this relation will tell me if rho is constant. So for a constant density, that the radius, or the Lorentz factor, goes down like the radius to the minus 3/2. Okay? This is similar to how, in here, the velocity would go down with radius as the radius to the minus 3/2. So instead of velocity square here, I have c square gamma square in here. So some people, when they want to do both regimes in one shot, they say this is either the Lorentz factor or the velocity, and to make them both, you can do this. So you see, when the speed is very relativistic, beta is 1. So you get what we had before, gamma proportional to r to the minus 3/2. When the speed is very small, gamma is 1. So you have that the velocity goes like r to the minus 3/2. So this is a smooth thing that connects both regimes. Why is that funny? Okay, just cute. Okay. If you do it accurately, you can use self-similar solutions and get the correct coefficients in here. This equation, as I tried to explain, is not accurate for many reasons. Both because, let's say in this version, that r over t is not really the velocity, it's just an estimate of the velocity. Also, the velocity of the fluid behind the shock is not equal exactly to the velocity of the shock. It is some fraction of that, and it also has a profile behind the shock. And there is thermal energy, which I haven't included. It's on the same order of magnitude, but it's not the same. So all these things would put in here some factor which we don't know. And it so happens that when you do correctly both this, which is called the set of Taylor solutions, if you do them correctly with all the coefficients, or this version, which is called the Blandford-McKee solution, I think from 76, then you get that the coefficient that comes into the equation are also quite similar. So this is not a bad way to join those two relativistic and non-relativistic cases. Okay. So here, it was really easy for me to tell you how the radius changes as a function of time. Here I only told you how the Lorentz factor changes as a function of radius, but what I really want is how things change as a function of time. But that immediately leads us to another discussion, which time, right? Now it's relativistic, there are many times. So there are 3 of them, I think Tzvi mentioned, but let me do that again. So we have a shock wave that came out of this point and arrived to this point, almost at the speed of light, right? So how long does it take to arrive from 0 to a distance r? R over c. In which frame is this time? Our frame. The frame in which we see the shock wave propagating at the velocity of light. Okay. So this is fine. It's a bit smaller, it's a bit longer than that because the shock wave doesn't move exactly at c, but almost that. Okay. There is another time, which I will not talk about too much. This is the time in the local frame of the exploding stuff. And this is longer by a factor of gamma. Shorter by a factor of gamma. From here to here, it's just a relativistic transformation, special relativity. Okay? This is Albert Einstein. Okay. Now there is another time, I'll mark it as capital T, which is the time that the observer will measure, the observer that is standing here, of the arrival of the photons. Okay, why is that any different from this one? So both this time and this time are measured in the same frame. They're in the lab frame. The frame of this guy, also the frame of the exploding source. I'm ignoring now the cosmological redshift between those two. Okay, so forget that part. The only relativity stuff that I'm doing is the expansion of the explosion itself. The universe is static for me. Okay, so what is this time of arrival? So first, it takes a lot of time for the photon to arrive from here to the observer. But this we don't care. This is a one-time additional time, d over c, that it takes a photon to come from here to the observer. And we mark t equals 0, this capital T equals 0, the time that the photon came from the explosion at the time of the explosion to here. Okay, so maybe I should write this. When it arrives to the observer, this defines t equals 0. And now I want to know if a photon came from here and arrived to the observer. This arrives at time t. So it's the difference between this arrival time and this arrival time. This photon came out from this explosion at some time, t, which is roughly r over c. But I want to know how much later, after this photon, it arrived to the observer. I'm not doing any relativistic transformations here. It's all in the lab frame. So the transition between this and this capital T is Newton, no Einstein. Okay, so let's see. Why is that photon arriving after this photon? Because the explosion is moving almost at the speed of light, while the photon is moving at the speed of light. So when this shell is here and emitting this photon that we're interested in, the photon that defines for us t equals 0 has propagated, and it's now a little bit ahead of this. It's this one, actually. It is here at this time, and the distance between them is very small. Once both of them are emitted, they propagate. The distance between them stays, and the difference between the arrival time will be this distance divided by c. So what I'm interested now is what is this distance. Let's call it delta. And this t is actually delta over c. So what is delta? Is the distance between a photon that came out at the time of explosion from the center of explosion to a photon that was emitted at some later time when this shell is at a distance r from the explosion. So this delta is the amount of time passed, this little t, which is roughly r over c, times the difference in velocity between the two objects, the photon, which moves at c, and the shell, which moves at some velocity v. So delta is t times c times 1 minus beta. And as Tzvi already mentioned, 1 minus beta, this beta, v over c, is related to the Lorentz factor gamma. So beta is about 1 over, for very relativistic stuff, the Lorentz factor is very high, beta is very close to 1. But the difference between beta and 1 is 1 over 2 gamma squared. Okay, this is for very high Lorentz factors. So this is about t times c is about r, and 1 minus beta is 2 gamma squared, 1 over 2 gamma squared. So I can plug this in here, and I get r over 2 gamma squared c. So you see that all these timescales, these 3 timescales, they all have r over c. One is just r over c, one is that divided by gamma. This is due to Einstein. Special relativistic transformation, Lorentz transformation from here to here. And this one has nothing to do with relativity. So how did I get a gamma if something has nothing to do with relativity? Just from the fact that I use the difference between the velocity of the shell and the velocity of the photons. Newton could have done this calculation from here to here, if he knew that the light is moving at some finite speed c, and get this answer. Okay, so when we measure the time of arrival of photons in the lab, we measure this. This is the thing that allowed to solve the compactness problem that Zvi alluded before, that the radius can now be 2 gamma square CT rather than just CT. So you're allowing much bigger sources, showing the same short time scale variability, solving the compactness problem. Okay. So if I go back to my explosions here, or the relativistic version in here, I can now translate this to how the Lorentz factor or the radius depend on time. So I just have to plug this relation between radius and Lorentz factor and time to either get rid of the Lorentz factor or the radius to get each one of them as a function of time. So let's get rid of the radius, for example. So I have gamma proportional to r to the minus 3/2. If I get rid of the radius, I have the radius is t times gamma square. So I have gamma to the 4 proportional to t. Okay? Same thing, you can get the radius. Okay. So what I got is that from this conservation of energy, the conservation of energy was rho r cubed gamma square c equal E, together with time is equal to r over 2 gamma square c. The combination of these two allows me to get how the Lorentz factor and the radius are changing with time. And the Lorentz factor is proportional to t to the minus 3/8, and the radius is proportional to t to the 1/4. Okay? So this is a summary of these results. So we can do the same thing for changing density, for wind density, but I think you can all do that by now. Okay, so the second thing I want to add on that is synchrotron radiation, okay? Because most of the afterglow emission is synchrotron and inverse Compton radiation. So first let me tell you about synchrotron radiation in general, maybe also about inverse Compton radiation. Synchrotron radiation is the radiation you get when you have an electron moving in a magnetic field. I didn't check that the directions are right. I'm okay? Okay. So this is the magnetic field B, and this is the electron. And if it's not relativistic, then the centrifugal forces this is the acceleration if I know that the electron is moving on a circle. This is the force towards the center, is V over C, the charge of the electron, let's call it QE, times the magnetic field. Okay, so the magnetic field, the Lorentz force, provides the centrifugal acceleration, and that gives you the frequency of rotation, V over R, which we call omega, is EB or QE B over M electron C. So when you specify it like this with omega, the velocity of the electron does not appear in the answer. Yes? There was no jet here. This is a spherical explosion. Jet will arrive later.
So this R by 4 by 3 pi r cube is considering that you're talking about a
Spherical explosion.
it's not potential. This 4
Spherical explosion. No jet. Jet in half an hour. Okay. So the cyclotron frequency is V over R, QEB over M electron C. Okay. What do I have to change if the electron is relativistic? Just the mass. Same thing. I can just plug instead of V, C, but V cancelled anyway. The mass is now gamma. Let's call it gamma E, sort of to say that this is the Lorentz factor of the electron, not the Lorentz factor of the shock wave that we were talking about before. They are related, but it's not the same thing. So then the omega of the synchrotron is actually smaller by a factor of gamma. The electron becomes heavier, and it's harder for the electron to spin in the magnetic field. So it moves on a slower pace. It completes a circle on a longer time scale. Okay. But what I'm interested in is the radiation that I see, not the time scale that it takes the electron to make one orbit. In the non-relativistic case, the radiation that I see is on this frequency. It's on the frequency of the orbit of the electron, because I feel the electric field during the whole revolution, and it changes basically sinusoidally on this frequency. But as the energy of the electron is growing and it becomes relativistic, the electric field that the electron creates at any moment is more and more beamed around the motion of the electron. So you should think, if you want, heuristically, as this electron emitting radiation that is mostly directed towards the direction of motion within a conical region of size 1 over gamma. There is also emission to here, but it's weaker. So what happens in the non-relativistic case, so the difference between the up and the bottom here, this is non-relativistic, this is relativistic. Here we'll get an electric field, E, as a function of t, which is sinusoidal on this frequency. Here, of course, the whole thing is also going to be periodic on the same frequency because the electron trajectory is periodic. But the electric field is not going to be sinusoidal anymore. So this is now T. This is the electric field. And you'll get something that has a short, I'm not sure exactly how it looks around some time, but this whole thing is the duration of the circle of the electron, okay, 2 pi over omega, which is now longer than before. But the region over which the electric field is strong is now very narrow in time. It's at the time that the electron is directed towards the observer. Let's put the observer now in here. It's trying to watch this electron. But because the radiation, or you can think of the radiation from the electron as coming beamed, it's only when the electron is passing through 1 over gamma in here that you see a significant amount of electric field coming out. So this makes this narrow again. How narrow? This is what I want to try to answer now. So what do you think? So I'm trying to estimate this. So which fraction of the circle is this? Out of the whole circle? Yeah, 1 over gamma, maybe 2 pi's, but 1 over gamma roughly. This out of the whole thing. So you may be tended to say that the duration of this out of the duration of this is 1 over gamma. But as the electron is moving, if you think now of this time scale we discussed in here, if you're an observer here trying to feel the electric field coming from the electron, but the electron is choosing the electric field that is shooting out almost at the speed of light. So the time is contracted again from the real time by a factor of gamma square. So the actual duration here for a given observer that is stationary, because the electron is chasing the radiation that it emits, is shorter by the real time by a factor of gamma square. So the real time that the electron spends in here is shorter than the whole time by 1 factor of gamma, but the duration of the signal that we see is shorter by 2 more factors of gamma. And therefore, that leads to a frequency that is bigger than this by 3 factors of gamma. So let me summarize. When you have a relativistic electron moving in an electric field, the time that it takes the electron to make 1 revolution is longer than if the electron was non-relativistic. When it's non-relativistic, this time is energy independent. But as it becomes relativistic, the time scale starts to be longer and longer. But for any given observer, the time scale for which it feels a significant electric field is actually shorter even than the non-relativistic time scale by a factor of gamma square. So there are many factors of gamma that went in this discussion. There is the non-relativistic result for the time, which is also the frequency of the radiation you will see. Then that time is longer by a factor of gamma, or the frequency is smaller by a factor of gamma for a relativistic electron. But then when you translate that to the duration where you feel a strong electric field, you get 3 factors of gamma back. Is this point clear? So what we learn from that is that the frequency h nu of radiation coming from synchrotron is what you would expect from non-relativistic electrons times gamma square. Okay, because 1 gamma here and 2 gammas and 3 gammas here, you're left with gamma square. Okay. Of course, you can do an exact calculation of this, get a full spectrum, all that stuff, but this will be too complicated for us now. There is a way, or a heuristic way, to think also about the power that this electron emits. The power that a single electron emits in synchrotron radiation. And this goes as follows. Again, it's a heuristic way, but it's a way that is very easy to remember. If you think about it this way, you'll remember it. Yes?
We see here that the angle of the electric field should be much narrow when we move to relativistic.
Can you see it from where? No, I just said it.
Okay, so it's not something that we've seen why it happens.
No, I didn't say that. So when you have something which is isotropic in one frame, okay, so take these vectors. Let's say they are velocity of photons. Okay, so there is a flashlight, and it emitted photons in all directions isotropically. And ask how is this picture looking in another frame that is moving relative to this with a Lorentz factor gamma. And let's say that the motion is in this direction. The answer that you will get is the following. The one that went straight forward remains forward. The one that went straight back remains backward. You can't, from symmetry, you cannot change that. Okay? But all the others, the one that was 90 degrees here, so maybe I should name them. Yeah. So if this is A, B, C, and D, this is still A, this is still B. This is now a very energetic photon. This is a very weak photon, so even though it exists, you can forget about it. C and D, which bound half of the photons, are now 1 over gamma away from the forward one. Okay, and all the other ones that I haven't named, they're also here. And some of the ones that went backwards, they're still here, there, and they're weaker and weaker the farther you go back. So this is the picture of a beamed object that is isotropic in its own frame. Okay? So that's why I put this 1 over gamma. Thank you for the question. Okay, I was trying to tell you about the power. So to think of this power, it's actually easier to do the inverse Compton case, the scattering of light by relativistic electrons. If you have an electron moving with a Lorentz factor gamma, and it sees a photon of energy h nu, and the photon sort of happened to hit the electron and bounce back, h nu prime. H nu prime is equal to roughly gamma square times h nu. Okay, let's do, before we go into why gamma square in here, let's do the non-relativistic analog of that. Okay, suppose you have a ball and a racket, and you hit the racket. You hit the ball with a racket, and the racket had velocity v. What is the velocity that the ball will get? If the racket is infinitely more massive than the ball, it doesn't feel the ball, it just moves. 2v, right? Why 2v? So here's the racket. Here's the ball. The racket was moving with velocity v. The ball was stationary. We move into the frame of the racket. So we're just changing frames. The racket is now stationary. The ball is moving with v. In this frame, conservation of energy tells us that the ball bounces back with the same velocity. This is v prime. And when I will transfer this back to this frame, I'll have to add v to this v. So I'll get that v prime is equal to 2v. I can do the same argument in the relativistic case. I'll do it on the other side, or here. So if I move to the rest frame of the electron, where the photon was moving towards the electron, so I will get that at the rest frame of the electron, this photon is more energetic. And in that frame, it is bounced back with the same energy. But to transfer it back to this frame, I have to give it another factor of gamma. So I get a gamma square. Okay? In a way, this is the same gamma square that we saw in the equation for energy, this one. Because you could have thought of this shockwave that expands as a racket that hits the protons that are standing in the environment. And when it hits any one of them, each one of them get a Lorentz factor, which is gamma square. Except that before I counted it differently. I said that one gamma is thermal and the other one is bulk. But it's the same gamma square. Okay, so if we know that the cross-section of interaction between photons and electrons is the Thomson cross-section, which is true for low energies. So I can think of my electron as an entity with a cross-section sigma Thomson, which moves almost at the speed of light, maybe beta times the speed of light, but this beta is close to 1, so it's not really important. So with a unit, within a unit time, it goes through a cone, a cylinder of volume sigma Thomson times beta c. And any photon inside it, it scatters and gives it energy by a factor of gamma square. So suppose there are photons in here. which my electron is bouncing. So per unit time, P inverse Compton is this volume of cylinder, which is sigma Thomson times beta C, times the energy density of the photons inside, let's call it U photons, times gamma square. Again, what is this? This is the volume of the cylinder per unit time. This is the energy in that cylinder. So this is energy density. So energy density times volume is the energy of the photons in the cylinder. This is the energy of the photons that the electron scattered per unit time. Each one of them boosted its energy by a factor of gamma square. So this is the inverse Compton emission. And the simplest way to think about synchrotron radiation is to say that this is exactly the same, except that the photons are the energy density of the magnetic field. So I'll just copy this, and instead of few photons in here, what should I write? B square over 8 pi or something like that, yes. And if you want to do this accurately, this equation is almost correct. There is a 4/3 here, gives you the exact answer. And the 4/3 will come correctly when you average over the possible directions of the electrons. Because when we did that before here, we assumed that the ball and the racket are moving towards each other. And also when we did it with the photon, in order to get a boost of gamma every time, you need to assume that they're moving towards each other. If they will move at some angle, you'll have to average over all these angles. That gives this 4/3. Okay, so the power of electron is 4/3. Sigma Thomson, C, I don't need the beta because it's 1. Gamma square, B square over 8 pi. So this is the frequency. Actually, for this to be the frequency, I need the H in here too, because this is a frequency. And this is the power, energy per unit time, that a relativistic electron in a magnetic field is emitting. Okay. So what do we want to do with all this now? I would like to understand not only what is the emission that is coming out from a single electron, but from a distribution of electrons. So here's the story that we say when we have afterglows of GRBs. We're saying that there is a shock wave that is accumulating that mass. It accelerates the electrons that it collected to all kinds of energy, some distribution of energy, and we model it in the following way. This is the Lorentz factor of the electrons. This is the number of electrons per unit Lorentz factor. We're saying there is a minimal Lorentz factor, which we'll discuss in a second, and a parallel distribution of electrons above that. Okay, that's the model. And what I want to calculate is what happens if you put this distribution of electrons in a magnetic field B. Each one of them is emitting synchrotron radiation, which we just discussed. And I want to collect what will come out from all of this. I'll give you the bottom line, and then we discuss it. So the bottom line is frequency, F nu, energy per unit time, per unit frequency, per unit area in the detector, somewhere away from the electron, or the explosion. Now it's an astrophysical situation. Okay, this is not yet really the full model of afterglow of GRBs, because I still have to put a relativistic bulk, relativistic motion to all of this, but we'll do that later. So right now I have electrons whose thermal Lorentz factor starts from some gamma mean. And they are distributed according to this, all embedded in some magnetic field B. Okay, so we already saw that each electron will have some frequency that it emits. So let's say the frequency that corresponds to gamma mean is nu m. And we calculated before the amount of energy that comes to that frequency. So that will give us some signal in here. Then we have to spread that over 4 pi d squared, d the distance to the observer, and we'll get some emission. If we'll take another electron from here, it has a higher Lorentz factor. Therefore, it will emit at higher frequencies, proportional to the Lorentz factor to what power? 2. We had that before, right? It's here. 2 powers of the Lorentz factor. It will also emit more energy per unit time. And we'll get a power law that corresponds somehow to this power law because it will, the number of electrons here is fewer than the number of electrons here. So if I want to see that power law, what is that power law? That came out from this power law. I can do the following estimate. Do you see it? Where is the eraser? Okay. So the number of electrons at any range of Lorentz factors is gamma E dn dE, dn d gamma E. That's the number of electrons. Each one of them is emitting at a total energy of 4/3 sigma Thomson C gamma electron square B square over 8 pi. Right? So this is the number of electrons at some range of Lorentz factor. This is the energy emitted by each electron. If I divide that by the typical frequency, which was this, then I get the energy per unit time per unit frequency, which is what I'm plotting in here. Or divided by 4 pi d squared, the distance of the observer, to get it per unit area as well. Right? So 2 gammas here cancelled, and then the only gammas left are coming from here. And this is proportional to gamma to the minus p plus 1. But if I want to write that as a function of frequency, not as a function of Lorentz factor, because frequency and Lorentz factor are related with a square, then this is proportional to me to the minus p minus 1 divided by 2. Right? Because when I did it with gamma, I got minus p plus 1, but as a function of frequency rather than gamma, it's this. Got it? Okay. Now, I actually didn't do what I told you. I told you I'll give you the bottom line and then explain it, and I started to explain. So let me say the answer first. So the spectrum overall is going to look like this. Okay, 4 regions. Each one is roughly a power law, connecting at some interesting frequencies which we want to discuss. So what I want to complete now is what is the slope in each one. I don't know how many I'll have time to do. And what are the break frequencies. So some of them I will just tell you, and some of them will actually calculate. So this power law we already discussed. This comes from the emission of each of the electrons in this. And in principle, you can think that this continues forever. But there is a problem here. The energy of each electron is proportional to the Lorentz factor of the electron. The energy of each electron is gamma electron, m electron c squared. Right? Yet the rate at which it emits radiation is proportional to the Lorentz factor of the electron square. So when you go to very high energy electrons, they emit the radiation, they emit the whole energy on a shorter and shorter time scale, because their total energy is only proportional to 1 power of the Lorentz factor, while the power that they emit is proportional to 2 powers of the Lorentz factor. So high energy electrons, they cool fast. So at some point on this distribution, you will get electrons that are cooling faster on a shorter time scale than the age of the system. So even if you put those electrons in the beginning, after a while they won't survive. Okay, so to know the correction for that, you need to estimate the time scale of the lifetime of this electron, but we already discussed that. So the T cool of an electron with a Lorentz factor gamma E is gamma m electron c squared divided by 4/3 sigma Thomson c b square over 8 pi gamma electron square. That is proportional to 1 over gamma. So these electrons, they live for a long time, longer than the age of the system. So what I put in the beginning is what is actually there. These electrons, behind some critical value, these electrons live exactly the age of the system. These electrons are only there for a fraction of the time. What is the fraction? Proportional to 1 over gamma. Or if I want to state that as a fraction of frequency, frequency and Lorentz factor are related according to this. So because they are staying there for a shorter time scale, because they cool, I lose half a power of frequency. So instead of minus p minus 1 divided by 2, I have nu to the minus p over 2. Understood? So this emission is weaker than the extrapolation of this. That would have been the emission if the electrons will stay there with the Lorentz factor that I put them there initially for the whole time. But if they cool and they only live a shorter time scale, then I have to multiply by the fraction of time that they were still alive. That is a short fraction, the higher the frequency or the higher the Lorentz factor. So the ratio between this and this is this 1 over square root of nu. There is another way, simpler to get this power law directly. So the way I got it now is I asked how much do I have to change the extrapolation of the previous calculation. But I can calculate this directly even more simply, because it's actually very simple. I don't care about the synchrotron power. If I already know that this electron cooled, it means it emitted all its energy. So I just have to know to which frequency it emitted it. So I can do this calculation directly by saying the energy of the electrons in here. This is the number of the electrons. This is the number of the electrons in some range of Lorentz factor. The energy of each one of them is this. And all that energy is going into a frequency, which is that frequency. EB over m electron c times gamma electron square. So this, and that cancels. And you get that this is proportional just to that, which we assume is gamma to the minus p, which is nu to the minus p over 2. Okay, so more direct way to see it. So here I had to use the power, this equation, the power of the synchrotron emission. And to get this one, I could either correct that power to the finite lifetime of the electrons, or I can say all the energy of the electron is emitted and get it directly. Excuse me. Okay, what is happening in here? In here, it's the low energy tail of synchrotron emission of the lowest energy electrons. And this is slightly more complicated to show, but this goes as nu to the 1/3. So this is the property of synchrotron emission, not the distribution of electrons. Okay? So even if I had monoenergetic electrons, I will get this. Okay, and at even lower frequencies, the synchrotron emission is so efficient that it also absorbs the photon that it emits. So this is called self-absorption. Below this, what you actually get is more or less a black body with the temperature of these electrons. So you know how a black body spectrum looks in F nu as a function of nu. It has an exponential cutoff and the nu square dependence on the low frequency range. The actual expression here with all the coefficients is 2 nu square over c square times kT per unit area of the emitter. So this is the way to calculate this. This is 2 nu square over c square times, what should I put instead of kT? This is not really a thermal distribution, so we're sort of making this up, but what's the effective temperature? It's the energy of these electrons. So gamma E, gamma min, m electron c square. And what else am I missing there? The area of the fireball you're dealing with, r square divided by 4 pi, the distance to the observer square. So this is how you build this whole spectrum. So the model is super simple. There is only a single power law distribution of electrons embedded in magnetic field, and you get these 4 broken power laws. So if you actually want to make a calculation with this, we need a little bit more, because we need to know what is the magnetic field that we expect in these explosions. We need to know what is this minimal Lorentz factor. We need to know what is the actual distribution of electrons, what is P, and how many electrons are there, what is the normalization of all this. So some of it is easy. How many electrons are there? Well, we know we've just collected them from the surrounding. We know the total mass. So the total number of electrons is just rho r cubed divided by the mass of the proton. Right? So this is the total mass we collected. This divided by the mass of the proton is the total number of protons, and each proton has an electron. So this is the number of electrons. That gives the normalization of this whole thing, and therefore the normalization of this. What is the magnetic field? And what is that minimum Lorentz factor of the electrons? So here, we don't really know, but we parameterize that in the following way. We're saying that the energy of the minimal electron is a certain fraction, we call it epsilon E, of the energy of the protons in the same situation. So the energy of the protons is gamma n proton c square. So let me tell you what's going on here. Do we still have that? No, we don't have that fireball anymore. Behind which one? This one? You follow the eraser all the time? Nice. Okay. So we had that fireball which moves with a Lorentz factor gamma. And you remember I told you that the protons ahead of it are stationary, but once they're behind the shock, they have a random Lorentz factor gamma. I didn't write it correctly. We'll fix it in a second. So they have a Lorentz factor gamma. So the energy of each proton is gamma m proton c square. If the electrons have comparable energy, equipartition between the electrons and the protons, then I need gamma electrons m electron c square to be roughly that. Since we're not sure that the electrons manage to get all the way to equipartition with the protons, I'm putting a fudge factor here. I call it epsilon e. And this is the fraction of the proton's energy that the electrons have. If they manage to get to equipartition, this epsilon e may be a half or something like this. Half of the energy in protons, half in electrons, maybe a third, because maybe a third of the energy in the protons, a third in magnetic fields, and a third in the electrons. And if they didn't go all the way there, maybe it's 0.1. Okay, so you see from this equation, the c square cancels, and you get that gamma mean, gamma of the electrons, is gamma times m proton over m electron. Gamma is the gamma of the shock. And this is the characteristic Lorentz factor of the electrons, which is the minimum one out of that distribution. Okay, so I told you how to calculate gamma mean. What do I do with the magnetic field? I can use similar arguments also to say that the total energy in magnetic fields is some fraction that I will call epsilon b out of the energy of the system. So I would get that b squared over 8 pi is the energy density in magnetic field times the volume that it occupies, which is r cubed over gamma, is equal to the energy as measured in the local rest frame. Okay, so let's see, there are a few things to explain here. B squared over 8 pi, we already know. This is the energy density of the magnetic field. Magnetic field as measured in the rest frame of the moving fireball. So I have to multiply it by the volume of this moving fireball. And the volume of the whole thing is r cubed, but in the local frame of the fireball, it's r cubed over gamma. And the energy in the local frame is also E over gamma. So that gives us the magnetic field. And again, I can put an epsilon b in here times this. So the magnetic field energy density is some epsilon b times the total energy of the system. Okay, so I think I gave you all the tools to calculate that broken power law. Because I told you what is the magnetic field. I told you what is the minimum Lorentz factor. From that, you can calculate this frequency. Above that, you already know there is this power law. At some frequency, you will move to that power law. Which frequency? The frequency at which the electrons are cooling on the edge of the system. Okay, so we wrote that equation. It was here. Oops. Where the cooling time, which is this, is equal to the edge of the system, call it T. That defines some critical Lorentz factor, gamma E. Then you can plug that gamma E in here, times B, which you calculate from here. That gives you that frequency. So we call this the cooling frequency, the minimal frequency, or the frequency of maximal flux. You can use this M either for minimum or maximum. Works both ways. And this is the self-absorption frequency, usually called nu A. Okay. Questions? Yes?
Excuse me, could you remind me how you get this cooling timescale?
Yes. I calculate the energy of an electron, a single electron, which is just the rest mass of the electron times gamma, divided by the power that a single electron emits, this one. More questions? Yes?
Did you also go over the GRBs?
No, I did not say. I said that this comes from the emission of a single electron or monoenergetic electron moving in this magnetic field. So when we, it's a bit complicated to show that, so I skip that. But it actually comes from electrons that are moving on different planes relative to the observer. So this electron that has a plane that you're in is the one that will emit most towards you. That one will give you this peak with some low energy tail, but it's steeper than that. And then other electrons, which are not including you in their plane of motion, will give you lower frequency at their maximum. And when you combine all those, you'll get that third. Okay, so it's a characteristic of synchrotron emission of different electrons. All could have the same energy. So the way I think of it is electrons with some Lorentz factor. They have a characteristic frequency, which we calculated in here. But there is also emission at other frequencies. Above that frequency, there is an exponential drop. So you can forget about that. But below that frequency, if you take all possible planes into account, you get nu to the 1/3. Nu to the 1/3, if you continue it too far to the left, to low frequencies, will go higher than black body emission of those same electrons. When that happens, the same synchrotron mechanism will absorb the radiation that it emits and truncate this flux into this. Yes?
How people thought of, like, these are gamma ray bursts, okay? And then to go from these observations to the idea of electrons moving in the magnetic field, like what drove the model initial idea?
Okay. So people see synchrotron radiations in many cases. They also see the non-relativistic case of cyclotron radiation in many cases in astrophysics. So these emission mechanisms were familiar. Okay. Other emission mechanism could be Bremsstrahlung, interaction between electrons and protons. In low densities, it tends to be not very efficient because an electron needs to meet a proton and accelerate in its vicinity. So usually when the densities are very low and you have relativistic electrons, you'll get synchrotron radiation. So you could have expected that based on low densities and relativistic electrons. And you expected relativistic electrons because we already knew from what Zvi said of the compactness problem that we expect that the whole explosion is relativistic. Yeah. So again, we see that in many situations. Magnetic fields in turbulent media, in turbulent conducting media, they tend to amplify and arrive to some equipartition with the motions. So we see that in the galaxy. The galaxy also has magnetic field whose energy density is not so different from the random motions of turbulence in the galaxy. So this builds on the same thing. Supernovae also have sometimes high energy emission, also modeled in this before the whole gamma ray burst situation started. So maybe that was a continuation of that. Yes?
You assume that mu A is smaller than mu M, which is smaller than, you assume
Yeah.
this order?
Excellent question. I assumed this order. But any other order is possible, right?
Yeah, I want to ask if there are cases in which you observe
So ask.
another order in the spectrum or...
Yes. Okay. Yeah, of course. Every order is possible here. So these frequencies, they're not constant in time. They evolve in time. Okay. Why? Because why we discussed how to calculate them. Let's say the magnetic field is evolving in time. Why? Because if I model it like that, and the radius is going up, then the magnetic field is going down with time. Also, the Lorentz factor cancels in here. Okay, so the magnetic field is going down with time. The age of the system is changing. So which one is the cooling frequency is changing with time because the cooling frequency are saying this is equal to T. As T is evolving, gamma E is changing. And also B is changing. So everything here changes. At very early time scales, this is the right thing. The order I plotted it for typical parameters we believe exist in gamma ray burst Afterglow. As time progresses, okay, so if you plug everything I told you in here, you will find that this goes down as T to the minus 3/2 for constant density environments. Actually, for both wind and constant density. This one goes like T to the minus 1/2 for constant density, T to the plus half for wind. Okay? So in a windy situation, early times would be, okay, forget wind. For constant density, this will be late times. Early times, this would be above this one. And at later times, even later times, this will drop below this. This is initially constant for a constant density medium. And there is a paper by Jonathan Granot who calculates the spectra in a more accurate way that I discussed in here under all possible combinations of orders. So if you change the orders, also these power laws may change. Okay? I can give you another example. Yeah, but I can just list the examples. It's not very productive. When nu m goes below nu a, then you have a nu square up to nu m, nu to the 5/2 up to nu a, and then those two. Maybe an interesting one, which is pretty relevant, is if nu c is below nu m. Let me draw that one for a second. So this is the power law distribution of electrons. This is now gamma E. dN dE that were injected, dN d gamma E. And the observed spectrum would be, so now the cooling frequency is below, so all these electrons are cooling, all of them. So all of them give me this power law. So from this frequency, I'll have nu to the minus p over 2. This is the frequency that I call nu m, corresponds to the minimal electron. The cooling frequency is now lower. And I have nu to the minus p over 2 directly above this frequency. Below this frequency, I'll get nu to the minus 1/2, a new power law, down to nu c. How can I understand this power law? So who is emitting this distribution of photons? It's all of these electrons that have cooled on the edge of the system. And even though I injected them to the system with these Lorentz factors, they have now cooled down to some Lorentz factor that corresponds to this frequency. As they were cooling, they gave this power law range of f nu. Why nu to the minus 1/2? Because the amount of electrons that emitted this, and that is the same. It's all the electrons. So when they emitted here, at any Lorentz factor, they had an energy gamma m electron c square times the total number of electrons, which is constant. There's no distribution like in here, because all of them cooled through this. And you divide that by the frequency over which they emit. It's a cool way to derive this. So that is proportional to gamma electron square. So this is proportional to 1 over gamma, or to 1 over square root of nu. And then below that, you'll again have nu to the 1/3 and nu square. Or you can think of self-absorption being here, or you can. So I think we're listing their 5 spectra, how they all evolve in time and in different orders. Okay, very good. I'm out of time, and I wanted to talk about a few more things. So I will skip. There's one thing I didn't tell you. If you actually want to get all these temporal dependencies, the t to the minus 3/2 and all that, you'll have to do this, but you'll also have to add the bulk motion, the bulk relativistic motion into account. That shifts the frequency up by 1 Lorentz factor of the whole thing. It shifts the power, and so on. And you will have to use all these. Okay, but I'll skip that. The last thing I want to mention, which is important, and Zvi already mentioned it before, is the jets. Also, Rita asked about it. So what happened if the explosion is not spherically symmetric, but the energy is collimated within some narrow range of opening angle? Let's call it theta naught. Okay, so the source, whatever this explosion is, it only emitted matter and energy in a cone of opening angle theta naught. How is that going to change everything that I'm going to see? So since I'm out of time, I'll do it very qualitatively. Okay, so I'm arguing the following. First, when it's very relativistic, when the Lorentz factor is extremely high, this will evolve. This explosion material will evolve as it interacts with the surrounding, as if it is part of a sphere. Okay? So this part does not exist, but this part, as it evolves in time, still obeys everything here. Okay? Why is that? Because there is no causal connection, I will argue, between the center and the edge. And of course, the center does not know that this does not exist. And there is only a limited range of material on the edge of the jet that will know that it's at the edge. The rest will continue as if it is part of a sphere. Okay, so what is that connectivity? So let's say that this explosion happened here, arrived to a distance r. How much time did that take? About r over c. This is in r frame. Note this is not the photon arrival time, which is smaller than that by a factor of gamma squared. This is the actual time that it took the shell or the explosion to come from here to here. In the local frame of the exploding stuff, the time is shorter by a factor of gamma. This is special relativity time contraction by a factor of gamma. Suppose now this side is trying to tell the center that there is an edge to the jet. Don't continue to evolve as if you're part of a sphere. And that information runs inside the jet at the speed of light. How far will it get? The time times the speed of light. So I'll call it r perp. Okay, so what did I do here? The time that it took the shell to come from here to here is r over c. The time in the local frame, where information is moving, is r over gamma c. If it moves at the speed of light in the local frame, then times c. This is r over gamma. So the things that are connected are things which are r over gamma away from each other. Or if you want to think of that as an angle, theta of connectivity, causal connectivity, is 1 over gamma. R perp divided by r. So each fluid element in that jet can only know about information of fluid elements 1 over gamma away from it. So if gamma is huge, let's say 100 or 300, Zvi told us before, that connectivity angle is tiny. If the opening angle of the jet is bigger, let's say it's 0.1, 5 degrees, 0.1 radians, 5 degrees, I'm just saying a number. This is actually a typical number for GRBs, but we'll talk about that in a few minutes. If this is 5 degrees and the whole thing is moving with a Lorentz factor of 300, things in the center will not know that there is an edge to the jet, and they will behave in the same way as before. But as time evolves, the Lorentz factor is going down, and the angle of causal connectivity is growing, proportional to t to the 3/8. Eventually, 1 over gamma, the angle of causal connection, is going to be equal to the opening angle of the jet. When this happens, at the time that this happens, the center already knows that it's part of a jet. The jet starts to spread and slows down faster than what we wrote there. Okay? So this will give you different temporal evolution. Okay, when is that going to happen? So we know how gamma depends in time, and we just equate this to that. And that gives you a certain time. So this is happening at a time we call t jet, which for typical parameters, I think it's something like 6 hours times the energy in units of 52 ergs divided by the density in units of 1 particle per cubic centimeter. To some power, I'll have to work it out for a second or look it up. And times theta to the 8/3. Or I can reverse this equation. Let me see if I had it okay. Yes, 1/3. Or observationally, I would like the inverse equation. I look on a gamma ray burst, and I see how it evolves in time. If it evolves according to this theory, it is either spherical or a jet with an opening angle that is bigger than 1 over gamma, so that it doesn't know that it's a jet. It behaves as if it's part of a sphere. At some time, I see a deviation from that spherical theory. I see a drop in my fluxes, which is faster, and I understand that 1 over gamma is just equal to the opening angle of the jet. Since I have a theory from the spherical theory, which is correct in the beginning, what is the Lorentz factor as a function of time, I can use that equation to tell you what is the opening angle of the jet as a function of the time that I've seen this jet break. Okay? So this is how we do it, and this is how we estimate from observations what is the opening angle of jets. And 5 degrees, 3 degrees, 1 degree, 10 degrees are typical numbers. Okay? I think Tzvi already mentioned, but I'll repeat that. There is a quantity we call E iso, which is the energy we estimate gamma ray burst had, assuming that the emission was isotropic. Of course, we cannot know the real energy that the gamma ray burst emitted because we haven't engulfed the explosion from all directions and see what it did. Well, Avishai has methods to look at it from behind and from the sides and whatsoever, but easy. But for most cases, we just have our little detector in here, and we count how many photons arrive to it, so we know the energy per unit area at our detector. We don't know the rest of it. If we assume that it's isotropic, we can multiply the fluence that we got in here. Fluence means energy per unit area integrated over all time in our detector. Multiply that by 4 pi d square, the distance to the source, we get the energy. We call that E iso, because it's the energy assuming that the explosion was isotropic. But now I told you of a way to measure what is the opening angle of a jet from the time that we see this jet break. So if I assume that now I have a jet that only occupies a finite region, then its true energy is smaller than this E iso by a factor, which is the solid angle of this divided by 4 pi. the solid angle of a cone with an opening angle of theta naught is pi theta naught square out of 4 pi. And people like to put here an extra factor of 2 because they think there is also another jet going the other direction. So this is theta naught square over 2. So this is E tot, which is smaller than E iso, maybe by 2 orders of magnitude, right? Because theta is 0.1 if it's 5 degrees. So this is 10 to the minus 2. And a combination of some burst for which there was enough information to infer this T jet, and therefore to infer the opening angle of the jet, resulted in an estimate of the true total energy. And what was found is that while this is varying tremendously by many orders of magnitude, this is also varying from one burst to another, but not as much. This is roughly 10 to the 50, 10 to the 51 ergs, while this is varying from 10 to the 51 to 10 to the 54. Presumably because some bursts are more collimated than other bursts. But the total energy budget is more constant. This is not a solid truth. It does change from one burst to another. But generally, it is true that the real energy is more uniformly distributed than the isotropic energy that you infer by just multiplying the fluence that you got by 4 pi d squared. Okay, I'll stop here. Thank you.